today's session with a talk by Mauro Mobilia from the University of Leeds. So when you want, Mauro, you can start.
Thank you very much. Thank you, Celia. Thank you, the organizer, for this nice meeting. It would have been a pleasure to be, well, in Brazil with you, but that's how it is. I hope it will improve everywhere soon. It's not really the case here, but so today I'm going to tell you about a dynamic network and how this is shaped by homophily and heterophily. So that has actually to do with some of what we heard yesterday from Marxista Miguel. So this is joint work with these three gentlemen that you can see. Xiang Li, who is doing his PhD with us in Leeds, and Alastair Ragledge, my colleague in Leeds, and Roy Zia from Virginia Tech. And it's based on two papers. One, the first one is going to be published very soon in PRE, and more technical details can be found in the second one that is on arXiv. So what I'm going to tell you about is concerned with dynamical networks, so where we will have agents holding two possible opinions, and these guys will create and delete links to satisfy preferred degree, right? And this will be done subject to some social easing-like interaction. That's where statistical physics enter, right? And we will ask the question: how does how do these interactions and the fact that they have a preferred degree will shape the network, right? So roughly speaking, the plan of the talk is the following. I will first discuss the symmetric case, so where we will have the two opinion groups that have the same size. So, and this is very nice because it's amenable to detailed analysis. And then I will discuss the more intriguing case of asymmetric group sizes, and we will see that there we can have different regimes and what we call an overwhelming transition. We will see what I mean. R is missing. And then I will discuss measures of polarization that will give and quantify the extent of division between the two communities. So by social interaction here, I mean homophily and heterophily. So homophily is, well, as the English word says, bird or feather flock together. Basically, you want to establish ties primarily, like in this cartoon, with individuals that share the same attribute as you, right? And heterophily, which is for which there is less empirical evidence, is just the opposite. There, agents try to reach out other agents that have that are dissimilar, right? So you chase the differences. But there are some empirical evidence of actually heterophily in information and in cooperation networks, which makes sense, right? You want to find people that have complementary skills. All right. So concretely, what we have is the following. We will have an undirected direct network of n nodes, right, labeled I from 1 to n, and well, each of them have a degree ki, and well, these agents in our model are zealots, so to say, right? So we have two groups, black and dark and yellow, light nodes, and well, these represent two different opinions, right? +1 or -1, say, right? So like in this cartoon, we have two groups, two opinion groups, right? And well, these will try to establish, well, we'll try to establish links between them to satisfy a certain degree, right? We say that in this system, well, this network, all agents have the same preferred degree that we call kappa, and we set kappa to be half an integer to be to enforce the system to always fluctuate, right? So not a single agent is always happy. It's always either it does always want to either create or delete node to satisfy its preferred degree, right? So we have fluctuating networks, and so I should emphasize that here, contrary to what we heard yesterday in Maxi Samuel's talk, the nodes here from, in this model are they don't co-evolve, right? So they are static. You allocate them with an opinion, so +1 and -1, right? And they stay in this state forever, right? So what is dynamic here is the process of creating and deleting links, right? So here we don't have rewiring, right? That's another key difference from what we heard yesterday. But the links are created and deleted to satisfy certain degree kappa, subject to homophilous or heterophilous or homophilic and heterophilic interaction as you want. So what do I mean by this? Well, this is shown in this cartoon here, right? So you have your node I that has degree ki, right? And if ki is greater than kappa, right, we will call this node a cutter, right? And what it does, so as shown in this cartoon, well, that's my node I, right? And the I will cut an ij link with a probability 1 minus j or 1 plus j over 2, right? Where j is our homophily parameter, right? And depending on the sign of j, well, it will prefer to cut similar or dissimilar nodes. Right? And the same way, if ki is less than kappa, right, this node will be called another, and what it does, as shown in this cartoon here, it will add a link, right? And this link will be either to a similar node or to a dissimilar node, right? So then this will happen with probability 1 plus j or 1 minus j over 2. All right, so, and well, because of these rules, when j is positive, right, it's strictly positive, so j is between -1 and +1, right? So when j is greater than 0, but less than or equal to 1, then, well, what happens is that you tend to add internal links, so links within the same group, right, similar links, and cut cross links, so links across the groups, right? So in this sense, when j is positive, well, the interactions are homophilous, or we favor homophilic interactions. Whereas when j is negative, right, what you tend to do is to add cross links, so links across both groups, right, and cut internal links, right? So you favor the creation of ties between the two groups, right? So in this sense, when j is negative, you have heterophilic interactions. And when j is 0, well, the cutting and adding is just random. So what is important to realize here is that, well, the nodes are, so to say, zealot, so they have fixed opinion. And what changes is, sorry, is the total number of links and the number of links that are across the groups. So we will call these cross links. So these are denoted L plus minus, so from joining a plus and a minus, and the number of internal links, so which is given by L plus plus and plus L minus minus. So these are links between plus plus and minus minus. All of these fluctuate, right? So here we don't have a rewiring. Sorry, and it can be shown that this system, well, is out of equilibrium, and therefore its stationary state is non-trivial. Right? So we will investigate. We are interested in effect of homophily and heterophily on the topology of this system. So what happens is, so on the top row, I show you some snapshots of the long stationary property of a system when M is 0. So when both communities are of the same size, and on the lower row, you see what happens when you have community of different sizes. And this is also for different values of J, right? So when J equals 1 and J equals -1, so these are the extreme cases, and these can be spatial cases, right? So when J equals 1, what happens is what we heard yesterday already, right? You have what people call fission or fragmentation. So basically, your system end up in two separate groups. So there we say there is complete polarization, because at the end, well, the dark dots have ties only within them, and the light ones, the same for the light ones. Quite the opposite when J equals -1. So what happens is that you have only crosslinks, right? So we call this anti-polarization, in the sense that all darks are connected to light. So they are only crosslinked, plus minus ties, right? And well, what happens when J? We are chiefly interested in what happens when J is between -1 and +1. Right, that's what you can see in these snapshots here. So what happens when J is between -1 and +1 is that you have you have a number of cross links, you have a number of internal links, right? And you want to understand how this varies with M and J, right? You are also interested in finding out what is the fraction of cross links and the fraction, sorry, of cutters and others. So what proportion of what fraction of your population is above or below this preferred degree kappa? And of course, you are interested in the degree distribution and trying to understand and quantify the level of polarization depending on M and J. So, well, since this looks like a random network, you expect that the average degree should be about kappa, right? And so that's what, in this example, kappa is 4.5, and that's what, well, this suggests. If you look at this, you see that almost all, nodes have more or less the same degree. But you see here in this last snapshot here, that when M equals 0.6, so there is a large community of dark dots and a much smaller one of light dots, and J is -0.6, so we favor really cross-link. Well, it turns out that the minority group has a much larger degree than the larger community. And this is something that we are going to discuss in the next slides, right? So to start with, we start with the simplest possible case with M equals 0. So there we have two communities of the same size, right? So the number of plus and agents equals the number of minus agents. And well, what happens is that if you look at the fraction of others, so number of agents having a degree less than kappa, quite rapidly, this attains stationary value, and you can look at the distribution of this of a number of others, and you see that it's essentially a Gaussian distribution with small fluctuations about it. So this suggests that a Midfield theory should be very useful to describe the property of the system, and that's actually what you can do. So what you can do is to look at the Midfield analysis by balancing the rate of change of cross links and internal links to obtain an expression for alpha and rho, so the fraction of others and cross-link across in your system. So if you look at the number of cross-links, so this is a number of links between the two communities, right? And you look at how this increases, right, according to the rule of to pick another, right? So you want to increase, you want to create a crosslink. So for this, you need to pick another, so that you will create a link. Then you have to pick an individual, an agent that has a different opinion than the one that you pick, right? And then, well, you need to establish a link between them, and this will be done with probably 1 minus j over 2. Now, so this is for the increase of the number of crosslink. If you want to look at how they decrease, then, well, what you need to do is to take a cutter, right? So this will be done with already 1 minus alpha, right? And this cutter, well, it has to select a neighbor, right? And this will be with the probability rho. And well, yeah, it has to cut that link, right? So this will be done with probability 1 plus j over 2. And you can do the same with internal links, right? And you end up with these two relations in red. You match them and you get an analytical expression for alpha, so the fraction of others, and the fraction of crosslink rho j, right? And these are shown as solid lines in these graphs, and the symbols are from simulation. So you see that the match is almost perfect, right? And you obtain interesting simple and interesting results. Okay. So you see that the fraction of others in the spatial case where your populations have your two groups have the same size is symmetric with respect to j. So if you have homophily or heterophily doesn't change, you have the same fraction of others. You also see that when you end up with when you are in the extreme case of j plus 1 or minus 1, right? The fraction of others is just 0. So this means that when you have only homophily, right? So you favor only creation of internal link when j equals 1 and crosslink when j equals minus 1. You will end up in a state where everyone is above kappa, right? So these are all girders. And in the case where j equals 0, right, the creation and deletion of links is just random, then, well, alpha is 1/2. This means that you have as many others and girders, right? Because this is, in this case, there is, you don't have neither homophily nor heterophily. When j is non-zero, you see from this expression that alpha is just less than 1/2, right? So that's interesting. This means that there are always more girders than others when j is non-zero. And you can also see that the fraction of there is this symmetry in the fraction of crosslink when rho of minus j equals 1 minus rho of j, right? And this has to do with the fact that when j equals 1, you favor crosslinks, and you end up when j equals 1, you end up with only with internal links, and when j equals minus 1, you end up with only crosslinks. So that's what you. Oh, and you have these special cases that I was just mentioned. Okay, so that's for the global quantities, rho and alpha. You can do better, and you can look at the total degree distribution, right? And for this, you can write a master-like equation for the creation and deletion of node of degree k. So you write a master equation like this in the stationary state, right? And you can work out what the rate for adding or cutting a link is, right? For a node of degree k, right? So here the symbol h is the Heaviside function. Anyway, you can work out in a Midfield setting what is RA and RC are, and then you can solve the regression relation here, and you find the total degree distribution, right? And you get the following expression on both sides of kappa. You see you get an exponential of p of k with an exponent that changes depending if you are below, right, or if you are above your preferred degree kappa. The exponent changes. But interestingly, you see that there is symmetry. There is a symmetry j minus j, right? So here you have just j squared. So the exponent here depends on j squared, not on j. Right? So this is theoretical prediction are shown here as solid lines, and the symbols are from simulation. Now, from this, you can work out what mean degree and the variance are of your agents, and you see that that the mean degree is about kappa, as expected, right? So kappa plus some finite number j, right? And the variance is also of order 1. So, well, what this says is that the total distribution is about kappa when m equals 0, so when you have community of the same size, right? So, well, this is not very spectacular, okay, but we are going to see that things change radically when m is non-zero. Just a comment about this. Well, okay, so the total distribution is essentially picked about kappa, but you can also ask what is for a fixed degree k, what is the distribution q of a number w of crosslinks. So you fix the number of the total degree k, and you ask what is the number of crosslinks. And you can work out that this is a binomial distribution, right? Where this row, we found the row, where this row is the Midfield expression that we obtained before. And again, you see that there is a very good agreement between analytics, solid lines, and combination result from simulation as symbols. Now, this tells you that well, the variance of the distribution of crosslinks is extensive, so it is of order kappa, right? So it's not simply of order 1, like the variance of the total degree. Okay, so that's for the case m equals 0. Now I'm going to discuss the case where m is non-zero. So where we have community of different sizes, and for the sake of discussion, we say that the group of having opinion -1 is greater than the group of having opinion +1. So when you have this, well, you have to distinguish between the two, the fraction of others and girders and the fraction of links in both communities. So that's why we introduce alpha plus and alpha minus for a fraction in each group, rho plus and rho minus for the number for a fraction of crosslinks in both communities, right? You can see the result here. So that's alpha versus j, and that's rho versus j. In red, in green, you have as a reference, you have the result obtained when m equals 0. So you see that there is a non-trivial, the alpha and rho depend non-trivially on j and m. So these are for different values of m. Now, as time is flying, the most important and most interesting feature that we are reporting here, you see, is the fact that there are two regimes, two phases. One that we call ordinary, that essentially resemble the phenomenology that we just covered in the case m equals 0, with some significant quantitative difference. And there is what we call an overwhelming phase, which appears under enough heterophily. And in this case, what happens is that the minority group, so here in red, is overwhelmed by the majority. So what happens is that the majority establish a large number of crosslinks with the minority, and the minority is overwhelmed. And being overwhelmed, it consists only of others, and the fraction of others for finite J falls to 0, you see. And so when you have enough heterophily, the fraction, the minority consists of only quarters, right? This goes to 0. The fraction of others falls to 0, and here, and so the committee with holding opinion +1 here is the minority, and it consists only of and the links. It consists only of quarters having cross-link with the majority, right? So this, interestingly, this non-trivial behavior is well captured by a refined Midfield theory that we devised, and this is shown here as a solid line. It's not perfect, but you see it captures the shape of this curve that is non-trivial. So how about the total degree distribution? Well, you see, so here I show you the total degree distribution for each community, P minus for the majority, P plus for the community, for the minority, so for each group. And you see there are clear differences. And when you have homophily, like in P, yes, or if you have low heterophily, like in A, well, you still have this distribution that is peaked about kappa, that is here about 60.5, and it's essentially an exponential distribution about this kappa. But when you gradually increase the level of heterophily, you see from C, in C it's minus 0.3, and then in D it's minus 0.425. You see something happens here, right? And instead of having an exponential distribution, you start having a Gaussian distribution, right? So the red moves to the right, and at the end, under large heterophily, right, like in E and E and F minus 0.5 and minus 0.6, well, you have very different distribution, right? So the majority is still distributed exponentially about kappa 60.5, whereas the minority in red is distributed, has a Gaussian distribution peaked about 150 here, right? So much larger mean degree for the minority.
Sorry, Mauro. Yes, Mauro, less than 3 minutes left.
Okay, so this is because of this overwhelming transition. So just in the 3 minutes that are left, so okay, we are able to predict the transition line of this transition between this ordinary and overwhelming regimes using our Midfield theory by just predicting when this happens here, this transition happens there. Okay. Perhaps a few words about polarization. Okay, so let's see here. So we wanted to understand to what extent the division between the two communities depends on J, right? And we wanted a quantity that give us -1 when the system is antipolarized. So when you have really two systems and the bipartite graph when you have indeed of both parties talking to each other, talking to someone of the camp, and polarization 1 when we had this fragmentation of fission, so two separate subgroups in a sense, right? And we want to have zero polarization when J is 0, right? And when the links are totally random. So typically, polarization is measured in terms of like looking at the fraction of clustering, right? So the typical measure is what we call lambda is 1 minus 2 rho, and this works well to capture the extreme case where J is +1 and -1, right? So this gives the right behavior, plus and -1 as expected. But when j equals 0.
I'm sorry, Mauro, but we are reaching the time limit. Please.
Okay, well, just to tell you that we have another measure in terms of point degree distribution, and this predict right behavior also when j equals 0. And here you have the two measures, the pi that we introduce and the one that is usually used in the literature. Okay, so let's skip and go to the conclusion. So do I have time for the conclusion, or should I just leave the slides like this? Okay, well, so in short, we looked at a fluctuating out of equilibrium two-party network, right, subject to two forms of social interaction: homophily, that like similar, and heterophily, like dissimilar. Our system is not characterized by rewiring, but by creation and deletion of links, right? Preferred to satisfy preferred degree. So we have found that when the group have different size, the system under enough heterophily undergoes what we call an overwhelming transition, by which the minority is overwhelmed by the majority, and the degree distribution there is Gaussian, with a degree distribution that is much larger than kappa. There are still many open questions, two of which are, well, what happens when you have not the same preferred degree for all agents, right? When you have k I, and well, to relate to what Max Samingel told us yesterday, what happened when you have coevolution of nodes and links. Okay. So perhaps I should stop sharing, or
yes,
are we
thank
doing?
you. Thank you, Mauro. We need Serge to share the screen. There is no more time for questions, but there are some questions in the chat that you can reply there, or in the interval, in the break we have. Okay.
Okay. Should do I have time? What do you want me to do? Do you want me to take questions, or should I just?
No, it's not possible now, but you can answer in the chat by written, or or in the break.
Okay. Serge,
you can share the screen.
Okay, so can
I will tell you, Serge, when 5 minutes are left, but it's good to leave this time for questions.
Yes.
So can you share the screen?
Yeah, yes.
The next talk is by Serge Galam from SciPol, France. He's going to talk about his prediction on the second Trump non-victory.
Can you see?
Yes.
Okay, right. And the problem, I don't see. Okay, so in September 12, I gave a Zoom talk in which I predicted Trump victory for the November election. And as we all know, actually Biden won the election. So my prediction was wrong. Now the question is, what was right, if something right in this failed prediction? Before going on, I would like to make this statement about sociophysics, which is about building a hard science approach to model social and political phenomena. And then in such a process, making prediction about real event is the key to art science. So the process is not a one-time shot, but rely on accumulating prediction, both right and wrong. So more precisely, I was predicting a narrow Trump victory. And to evaluate what went wrong with this prediction, I need to answer the following question. What was the amplitude of Biden victory? A large Biden victory would require revisiting the model with some important feature being missed. However, tight Biden victory would be coherent with the model, putting the error in the estimate of the respective proportion of the model parameter. So the main question here is, what is the amplitude of this victory? If we focus on the national vote, this is misleading, even if Biden got 7 more million ballots, because the American system is rather peculiar, and it is the Electoral College which elects the president. Now, if we look at the electoral vote, Biden got an advantage of 74.
Sorry, the slides are not moving.
Yes.
We only see the first. Now it's another slide. But your microphone is off.
Oh, so you see the slide. Oh, yes. Now, so I was saying that what is important is looking at the electoral vote, and then we could think that 74 votes were a substantial advantage for Biden. But actually, it's also not so true due to another peculiarity of this electoral vote system where the winner got all. Now, if we look at 3 swing states, Arizona, Georgia, and Wisconsin, we can really prove why Biden won on the edge. In these 3 states, the excess of ballot in favor of Biden amounts for only 10,000, 11,000, and 20,000 votes, which represent very tiny proportion of all the ballot. So now I will show you why his victory was really very tight. I will present an hypothetical scenario which is set to illustrate how tight and fragile was Biden's victory. It does not mean, of course, that Biden's victory is not clear. He did win, but on the edge. And what I will show that indeed, if we had only 21,000 Biden voters, which would instead as vote for Trump, Trump would have won the election. So if I will take on these 3 states half of the difference, saying they will change their ballot for Trump, actually this would mean a shift of 21,000 voters from Biden to Trump. And then if we move to the Electoral College, Biden and Trump would have been at a tie with 269 seats for everyone. And here we have another peculiarity of the American system. In case of a tie at the Electoral College, actually it is the House of Representatives which elects the president, but it is the House with only 1 vote per state. So we would have 100 votes. And it happened that Republicans had a majority of 51 votes till January 18, and then a tie from January 20. And the president validation was held on January 10. So
I'm sorry, Serge, but the screen is frozen.
Excuse me?
The screen is not moving. We are always seeing the same.
So there is a real problem here. Let's see.
Can you try forward and backward to see if it's moving? Yes, now it's moving.
Okay. So you did not see all this thing?
No, I listen.
Oh, okay.
If you can explain again rapidly, perhaps it helps.
So I was saying that what was important to evaluate the nature of my error in the prediction was to find what is the amplitude of Biden victory. And then if we look at the national vote, this is misleading because the American system, as I just mentioned, is different, and it is the Electoral College. Now, the Electoral College, Biden has 74 additional votes. However, by looking at these three swing states, Arizona, Georgia, and Wisconsin, having only 20,000 voters, which will shift from Biden to Trump, would have made Trump win the election. Because what is very interesting, that in case of a tie at the Electoral College, which we would have got with 21,000 voters shifting their vote, that at a tie, it is the House of Representatives which elects the president, with every state getting one vote, which means 100 votes. And the Republican had the majority of 51 till January 18, and the tie from January 20. But the validation of the president was on January 10, which means that the Republican would have designed Trump. So indeed, Biden did win on the edge. So this is in this sense that the prediction was almost right, even if the consequences are huge. And it was much more close in terms of amplitude of the pole, which we are predicting a blue wave. Now let's go to the story and the model. Using the same model, I had a successful prediction in 2016 and a failed prediction in 2020. And then it's interesting to understand what makes this different outcome. The model was the same, but of course the parameter, the fitting of some parameter was different. So in the model, I can include three kinds of agents: floater, contrarian, inflexible. The floater, they can shift opinion, and they are also susceptible to prejudice effect, which I can integrate at a tie when I implement the dynamics, which is done as follows. I have two competing choices, A, B, with a P0 for A, 1 minus P0 for B. Agents are distributed randomly in small group. They are updated locally using majority rule with tie-breaking prejudice for even side, which means when I have 4 people, if I have 2A, 2B, they go either to A or B according to the majority of the prejudice within the group. Inflexible do not follow the local update. Contrarian shift to the other opinion. And then once you do such a cycle of update, agents are reshuffled and distributed again, and so on and so forth. Each cycle of update modifies the proportion of floater, P1, from P0 to P1, P2, and so on. And we'd like to see if this will move above 50% or below 50% for the winner. I solve the problem for group of size 4, and this is the update equation in which we have all these component, floater, tie-breaking, contrarian, inflexible. In 2016, I consider that the inflexible and contrarian were not going to be an important element, so I did not take them into account. While in 2020, I consider floater and inflexible, and I will explain why. To understand the effect, the separate effect from prejudice breaking and inflexible, let's first see what happened when I have floater with this prejudice breaking effect, and what is the importance of this K, which will give the probability to move toward either A or B at a time. And you see here that depending if K is equal to 0 or 1, I have either a majority collapse or a minority spreading, because I have a tipping point which is at 77% or 23%. When I am below the tipping point, the dynamics will take me more and more below towards 0. When I am above the tipping point, the dynamics will take me upward. Actually, in 2016, Trump finds something very interesting according to the model in order to modify the effect of this type prejudice effect. He was doing it in 2 steps. The first was making his shocking statement, which was infuriating people, and this rejection was making people to condemn the statement, and he was first losing support. But in a second step, this emotion, so this is my hypothesis, this emotional reaction was unfreezing deep locked prejudice, reordering the active prejudice that Trump benefit. Indeed, at the beginning, most of the prejudice were in favor of Clinton. So it is important to be able to benefit from the prejudice, even if you lose support. However, you need to be above the tipping point. Here is an illustration where I have an initial support of 24%, and instead here is taking K equal 1, K equal 0, and you see due to the difference of the tipping point, this 24% will go to 1 or either to 0. So Trump martingale was working when he's falling after making a shocking statement. When it falls, it stays above the tipping point. So then he was benefiting from the prejudice, while before he was not, but then he was able to recover and win. When his statement was putting him lower than the tipping point, he was losing. So what was important is that what he was doing could not be used by Clinton. So indeed, he has a major advantage, and then this makes that the precise estimate of the parameter did not matter. This is why the prediction went nicely. Now, for the 2020 election, many things have changed. First of all, the prejudice effect were different because after 4 years of President Trump, his shocking statement was not generating more indignation or emotion. Everyone got used to it. So the frozen effect, prejudice effect did not work. So then the spontaneous balanced prejudice was working. And this was based on fear, the fear of Trump or the fear of Biden, depending on which side you were. And also the COVID issue was important about the way to tackle it. Also, Trump mandate has highly polarized American voters. So we had millions of people which were blind Trump supporters, but also millions of people of anti-Trump supporters. So what was going to matter now was the difference in respective inflexible for Trump or for Biden. A is for Trump, B for Biden. And when we take this effect, this creates a very surprising dynamics because we have a shift from a tipping point dynamic to a single attractor dynamic. It creates 2 critical values for the difference in inflexible support. We have one in which A will win always. So this is a case where we have now a single attractor dynamics. And then on the other side, A will lose always. In between, we have a tipping point dynamics. So you need to start with an initial support, which is above the tipping point. So I will now show you an illustration, just one illustration, but you can find many cases. Here, A will lose with an initial support of 40%. And here, A win with an initial support, which is lower, 25%. what is the difference? Is that I have increased the support of inflexible for A from 14 to 20, keeping the difference the same, but it has a larger value. So in this case, we had the tipping point dynamics, and the tipping point was at 47. 40 is below, so A is losing. But in this case, it's a single attractor dynamics, and then the attractor is at 74. So even starting from 25, the dynamic will push you toward 74, and then you will pass the 50%. This is the other side. So in 2020, we had a combination of prejudice and inflexible. So what was going to matter is the excess in prejudice, which is at your benefit, and the excess of stubborn agent. So X, we already saw A minus B give this excess, and I write dk as K minus 50 to see the balance, which is giving an advantage for A or for B. So then both candidates for this election, which is different from the previous one, was competing on the same ground of this parameter of prejudice and polarization. So it was going to be around 0 for X, who will get more inflexible, and dk equals 0, who will get more benefit from the prejudice. So this is why this was going to give a tight victory, because we are around this 0 and 0 for both this important parameter. Some illustration. Here, I take a situation in which I have one attractor due to the inflexible. I have an initial support of 50% for A, and the X is minus 0.02, so a very small difference. However, there is a little advantage for A in terms of inflexible. And then I will vary A and B equally, which means here you see I have 20% inflexible for A, 25, 30, 40. And then when I increase A, I also increase B, keeping always this difference of minus 0.02. Here the attractor is at 65. Here it is at 53. As we have one single attractor, it means that this defines if A is going to lose or win. In this case, it will lose. When I go to 30%, I am just at 50%. So this is an Young election. Very small fluctuation will make the victory. And when I go to 40% for A, then the attractor move now down to 49 and A will win. We can have another illustration in which I have an initial support of 30%, A is 36, so this is rather high proportion of inflexible, and I will vary X and dk to preserve. This will keep a tight election at an Young election at 50%. So it shows that really things are very sensitive to what happened around this value of difference in X and K. So all this give Young election, which means a small fluctuation make the winner. This is another illustration in which I have always still one attractor. I start from 40% support for A, and then I have 40% inflexible for A, and I keep a difference of 6% in inflexible. So when I have X equal minus 0.06, it means that B, the proportion of inflexible for the B candidate is 34. And I just vary the difference in prejudice. 32, 40, and 41. Here I have a Young, and A win. So still very sensitive. So as I try to go quickly, the main conclusion, you can play with the equation and see all the cases which give this very, I would say, fragile result around 50-50, is that the winning strategy is was the same for both candidates. Then in each state, the outcome was supposed to be driven by these two quantities, x and dk around 0. They can go along the same direction to favor one candidate or the other, or they can compete one against the other. But it will be tiny excesses which will make the outcome. So then I had the problem of what to say about dk and x. When I was looking at stubbornness, then I found that blind anti-Trump supporters were not all automatically blind Biden supporters. You had many people which were on the left of the Democratic Party, which was not really very in support of Biden, but they were, of course, very strongly opposed to Trump. And also from what I was looking on social network and the TV, Trump was more involved on the ground to motivate its supporters. He was having large meetings with people there, while Biden, which was more safe and cautious about the COVID situation. So this gave me the feeling that indeed Trump was able to generate more stubbornness on his side. So this is, on these two remarks, my conclusion was that here and there in some state, Trump would get a little more stubborn people than Biden. Now, with respect to prejudice, I also was thinking that the fear of Trump somehow has been eroded because people knew how crazy he was and what kind of thing he can do. So it was not as the fear of Biden, which was among the Republicans, like he was going to install socialism, chaos. So it was more irrational phantasm. And I was expecting that irrational phantasm will create a little more fear than someone which is doing a crazy thing, but you know them. So here too, I was concluding that there will be a little more prejudice for Trump benefit. So giving a little more tiny advantage of dk positive and x positive in enough swing state, I conclude about Trump victory. It's important to mention that no appropriate data is available for defining this parameter. So really, it's this is a weak point of application of the model and what we learned from this situation. So with respect to the outcome, indeed, it has been tiny difference which made Biden victory, as I just proved it before. So from the model viewpoint, it was an error of sign on small quantities. Of course, the political consequences are huge and very important, but this shows that we have to work in the future more on how to evaluate this parameter more than on the model itself, which show more robustness. Now, about the conclusion on the political ground, first, also Biden did win. It was not a massive blue wave as predicted. Indeed, as I show, Trump could have won from another tiny fluctuation. However, usually when you have hung election, the loser accepts the result. First, he dismisses it and then he accepts. Here, Trump was very wrong, in particular in blaming massive fraud, according to this analysis. It was tiny fluctuation and not massive fraud which make this outcome. On the modeling ground, the same way that the 2016 successful prediction did not show the model is right, as we are in progress on this modeling, this failed prediction does not show that the model is wrong. Indeed, it shows that the model is quite robust and promising, but we need to design appropriate tool to estimate the model parameter. So more prediction to come, and try to find way to evaluate this proportion of inflexible, the proportion of various prejudice. So this is not so easy to design and evaluate. So to conclude, I think that all what this discussion and this situation show that we are today in our society at the point where it's very important to discover the law which govern our collective behavior, because it seems from this analysis that up to now we happen to be trapped by our unconscious archaic biases, and then our future is at stake, is understanding this effect. So this kind of modeling that we are doing, I think is very important and essential, but of course, going along prediction to be able to anticipate what could happen in many important situations. And we are all going to have important election in Brazil, in France in the coming year, and in other countries. So this is very important. So thank you, and I'm sorry it seems things did not work well for the presentation, but okay, that's it.
Thank you very much, Serge. There are some questions in the chat that perhaps you can. There are 3 minutes. We have 3 minutes. I shift the timetable, so I can. One is by Marcos. Marcos want to ask directly: Is your work valid? Is your model valid only in the USA system? How could it be adapted to other countries, Europe?
No, we can apply it also to other countries. So instead, indeed, the model for the American system was to apply it to every state, and then taking into account this electoral college. But in Europe, in our countries, we are like I think in Brazil also, it's a national vote. So then you have to apply it at once. However, we have different region and state and areas. So this is the way that has to be taken, because if you would say you have more inflexible for Bolsonaro in a given state, but it will be the opposite against him in other states. So this is the difficulty. You have to apply the model to different territories which are more homogeneous with respect to this parameter.
But there is another question rather related. Eric Cavalcanti want to ask, is proposed to apply to the next year Brazil election. Is there is some ongoing work in this direction to apply next year in Brazil? There's going to be an election, so
actually, yes, and we are having some collaboration with Nuno, which is also organizing this meeting towards the next election in Brazil to try to make some predictions. So we hope to be able. So it's a work in progress. It's quite complex because there are a lot of similarity between the Trump election of 2016 and Bolsonaro, but also very important difference about the social dynamics which was going on. But we are working on it, yes.
Okay, and also there are questions in the sense of external fields, like bots in social media or international opinion, such as in
yes,
what happens in Afghanistan, Iran, or
this,
it seems that the model is based on internal interactions, but also the external fields.
Yes. So at the moment in the model, the external effect can be taken into account by rescaling at some point the value of the different proportion for the candidate. So let's say you are at the moment having a proportion P for A and 1 minus P for B, and then you have a terrorist attack somewhere. So then this is going to act directly as an external effect and modify this value of P to another value. So the model, for the moment, is not able to say to which value it will go. This you need to use pole. And then when you have a pulse, you say, now, before implementing the dynamic again, I modified this value. So it is a one spot external change. So for the moment, you do it somehow by hand by taking this event into account. So this is what we need poles to calibrate this moment.
Okay, thank you. There are other questions in the chat, but the time is over. So I invite you to reply in the chat of Zoom or then in the break. So I now invite the next speaker. Thank you very much, Serge. The next speaker is Roberto Andrade from the Federal University of Bahia. You should allow him to, I think that you must stop sharing. Roberto, are you there? Can you share your screen? Roberto is going to talk about socioeconomic urban scaling properties in Brazil. Okay, you have 15 minutes in total. Try to leave some minutes for questions.
Okay. Okay, thank you for the organizer for this opportunity to present this work. Okay, I'm now working at the Federal University of Bahia. I have retired there, but I also work there as a volunteer and also at SIDAX, the Center for Integration Data on Health, which is associated to Fiocruz here in Brazil. The subject of my talk was published last year on PLOS ONE, and the authors, I would like to have used different colors to emphasize the fact that we have homophilic and heterophilic links here. Caio and I, we are physicists. The other three here, economists, and Mauricio, who is the leader of this center, is an epidemiologist. Okay, so the summary of the talk will go along this, and it is, of course, we are intended to analyze from a economical and from health point of view, what are the consequences of the heterogeneities in Brazil, regional heterogeneity, on the scaling analysis. Okay, we are living now in a quite overcrowded world with overcrowded cities. Cities here, we understand that go from 5 to 5,000 to some millions, 20 millions inhabitants. And of course, there are huge differences on behavior between those two types of agglomeration. And it's always pointed that we have great advantages for economy, infrastructure, services, creativity, and assistance programs when you live in cities. However, potential risk for enhancing problems like those that I just quoted here. The idea is that some complex systems are built according to very simple blocks, and that these blocks have some obey some scaling relationships. And these scaling concepts have been, through the years, an important pillar to fundamental relationships in complex systems. They started with allometric scaling relations in living organisms. More recently, they have been applied to cities. And what the assumption to be verified is that despite the specific historical and cultural background, cities are nonlinear scaled versions of each other. Of course, here I would like to say to call the attention, for instance, when you do isometric relations in living systems, you have some relations like the Kleiber law for metabolic rate that is valid from bacteria to whales, and but some other allometric studies show that some features are the better agreements find when you restrict the inclusion of animals or trees to some specific clades, the more investigated cases of mammals. And so we'd like that this could also apply within when you do similar studies on cities. And particularly, it has been mentioned that heterogeneities in large extension countries, like those 5 here, may lead to differences between cities. And so the key question of this work is how does in Brazil, these disparities, regional disparities influence the scaling relations. Here is a map of Brazil. We consider 5 different regional regions, geographic regions in Brazil. And the number of cities are like this, okay, northeast and southeast, about 30% of the share of number of cities. The south region, about 20%, and north and midwest, only 8% each, okay? If you go to heterogeneity from socioeconomic point of view, the Southeast has been historically concentrating more than 50% of the GDP, gross domestic product. Okay, here you have data from the census at each 10 years in Brazil that show the share of GDP in the different regions in Brazil, and also the share of the population, okay? The poorest, here is the GDP is not the GDP per capita, but if you consider the GDP per capita, the poorest region is the Northeast, okay? In the Northeast, if you show the recent the historical evolution, the Northeast has lost some population. The South increased until up to the 1970, and then started to stabilize at here around 15%. But the Amazon region, the North and the Middle East has been steadily increasing. Okay, so this is how the things have been evolved, and also an important important to see how the urbanization increased along this period. Okay, here we see that here we consider people in the city with more than 100 inhabitants, and you see that all of regions have been increased in their share of people living in large cities. Of course, now we do scaling analysis from the data. We estimate the less square estimation of y null and beta, and also perform the evolution of the Nadaraya-Watson kernel to see how good is this fitting. And we also measure the fluctuations on although I will not have time to discuss about the fluctuations, the work has this. And so we consider 4 different indicators, okay? Then national product, number of homicides, length of the water distribution system, and the number of high knowledge employees in the service sector. Okay, they characterize several. There are proxies for important aspects of the cities. We also evaluated this SSH, which is the heterogeneity on the regions. Okay, spatial stratified heterogeneity, which combines the variances intra-region and as compared to the variance of the fittings around all of the data around all Brazil. And so you have this, you see that they are very small and with exception with the water distribution system and the interpretations that Q values closer to zero, that the heterogeneity in the regions are even larger than those between them, okay? So we have to face that we have not only heterogeneity across regions, but also heterogeneities within regions, okay? We have, I will show here some results, okay? So for some regions, for Brazil, for South regions, and one of each different indices, okay? We have done this very through to all regions and to all regions, and the important is that they behave like this. They go from smaller for the water distribution system, which is typical, and then from GDP, homicide, and finally for the largest value of beta is for the number of employees in the high knowledge branch. Here we have show the longitudinal dependence of the regional scaling exponents. And this is the really amazing thing. You see that I have mentioned that that the southeast and northeast are the richest and the poorest GDP. But when you obtain the scaling exponent, they are much more similar, for instance, than from the southeast with the south region, which is the almost as rich as the southeast. Okay. This was an interesting aspect, and this appears, for instance, in the water distribution system for the Amazon area has the largest, the lowest value. Sublinear scaling exponents for infrastructural indicators is well known to be found in many places, but in the north region, despite the abundance of water, the large cities do not have a good water distribution system. Okay, so I just mentioned here some of the features that we found within for the values of beta that can be better concentrated there in our charts that we shown here. Okay. Here also the superlinear aspect of the employees in it's the highest in the northeast, for instance. That means that the inequality within the northeast region is the largest one. Okay. And okay, that's what conclusions. Of course, I have only short time to discuss that. What would you like to emphasize is that we have dealt with very good quality, high quality data from DataSUS and IBGE. Okay, and that's all. I think I could do in less than 13 minutes, Celia.
Okay, thank you. Thank you very much, Roberto. There are questions in the chat. I don't see any question, but you can raise hands too. Any question?
Okay, then let me.
Anything else you want to add, Roberto?
And what I really the important things are these charts here, okay, that show that first of all thing is that the along the years from the year 2000 to year 2016, there was no great changes in the scaling exponents. All scaling exponents remain okay. Somehow, some here, for instance, in the difference is the behavior of the south region that goes down. Okay, that goes down. That indicates that the small cities within the south region states are becoming more attractive to high technology employees. Okay, so these are features that you can, I think, that you can obtain from such type of scaling analysis. And of course, the fact that, as I said before, it was the most striking result for us is to see that an individual in the southeast region perceives the GDP, the difference in the GDP is much larger within the southeast than in the east. It's not the level of the GDP, okay? Of course, the level of GDP per capita in northeast is much smaller than in the southeast. But the difference across different city sizes are more alike from the southeast to the and northeast than as compared from southeast to the south, although both have the largest GDP, regional GDP in Brazil. Okay, that's the kind of
just one rapid question, Roberto. Have you continued or are planning to continue the study to the next years?
Yes,
5 years after the plot.
We are doing now together with colleagues from SIDAX and a regional and international network. We are doing the same for South America. Okay, so we are now doing scaling analysis for variables, health variables. The difference is twice. First, we extended it to South America and to Latin America, and also to concentrated more on health outcomes, okay, which is the major interest of the SIDAX Institute, okay.
Okay. Roberto, thank you very much. The time is over, but there is a question in the chat by Silvio that perhaps you can answer in the chat too, so that everybody
Thank you very much for your attention.
Okay, thank you. And next speaker is Sebastián Gonçalves from the Federal University of Rio Grande do Sul. He's going to talk about urban scaling related to COVID. You can share the screen. 15 minutes total. Everybody.
Okay, can you see my presentation?
No. Share the screen, please. No.
Okay. Share screen. Oh. Now,
okay.
Yes. Okay, I thank Celia, Marcos, and Nuno for this nice meeting, and thanks for letting me present my work. This title is kind of the original title is kind of misleading. This will be more correct. So first, let me present my my collaborator, Benur, which is a former master student, and this APL is where the result 100% are already published, and then there are other two preprints of all and ongoing work. So I'm going to talk about three topics related together: epidemics, which is mainly provided by the amount of data that came from COVID. and this allow us to make the urban scaling, and then we use a simple network theory kind to rescue and for interpretation of the results. So urban scaling, we have already listened to Roberto, to the nice talk, and we know what it's about. And I think there's going to be two other topics on the subject. So in simple words, it's trying to find empirical relations, like the size between the size of the population and the some observable, like the ones that Roberto presented. And Roberto already presented some cases in which alpha, and I'm using this letter to not be confused with the beta here, can be above or below 1, can be superlinear or sublinear. If there is no connection, and it can be another function, it's not restricted to power laws. And there is no connection, evident connection between y and x and the size, we say that the alpha is cannot be distinguished from 0, which is the case for epidemics. If we go to books, to the mainstream in modeling epidemics, I can quote this from Killing and Rouhani book. We say that in a few words, you cannot expect disease to be 50 times more infection in a city like London in comparison with Cambridge, because the 50 is the times the relation of the size of these two cities. So the conclusion in the books and in the Anderson and May and Murray books is that R0, which is connected with transmissibility, this is the basic reproduction number, is independent of the size. So this is called mass action hypothesis in epidemics. So to present my results, I want to say a few words about how data is aggregated. So in yellow, you can see here, which is an administrative city. For example, this is Porto Alegre, in which the city I am right now. And this red part surrounding is the suburbs. So these where people from the two places commute every day for work or study in normal time. So according to the OECD, these are called functional urban areas, and this is the way we are going to aggregate the data. In Brazil, they are called immediate region, which is equivalent. So, for example, this is a cartoon, this simplification. What we do, these are cases for one functional area around Sao Paulo. For the COVID cases after the first case, so these are days after the third case. So we pick up some time window, 30 or 60 days. From there we get the transmissibility or the R0. Okay. In fact, technically, what we do is we adjust these differential equations for the SER model, which is subtle exposed, infected, and recovery model, with these fixed times, the infection times, and the exposed time, and we let only the transmissibility or the R0 to vary as a free parameter, and from there we found adjusting to the time series of cases. Okay, for example, for United States we have this plot. The dots are obtained like in the analysis I mentioned before. And this graph represents the R0 on the vertical in the linear scale and the population sign in logarithmic scale. So all the graphs I'm going to present are in semi-log, log for the size. And we can see that there is a clear trend, which is represented by the linear, by this linear segment, a linear line, black. And in the case if the mass action should be valid, we will expect a cloud of points around horizontal line, which is clearly not the case. So mass action is not valid, and we have a logarithmic relation between R0 and the size of the city. So we want to now find why this is how. I mean, so now is where we use a very mean-field simple network theory. Before, R0 is factorized here as the transmissibility, which is called beta, and beta is in fact the product of the infection probability, which is the probability to get an infection from one other person, and C is the important quantity here, which is the per capita contact rate, which represents the interaction between people, I mean, in a city. This one is the one in which the size of the city can come into. And this tau is the time of the infection period. So now, by finding if C, the contact rate, is connected with N somehow, we can say that R0 is connected with N in the same way. And this is the simple Midfield theory. We assume that every person in the city can be potentially connected with everybody else in the city. So this I and J can be connected with the probability, which is the inverse of the number of people which are inside this disk, okay? And the people which are inside this disk is the density of people and times the surface of this disk. So this is why this probability is proportional to the inverse of the distance to the square, okay? So this is why we call it gravitational. Then we have to integrate in the whole city with some conditions at the short and long distance. And then we, because of the differential here, we end up with the integral of 1 over r, and this is why we get a logarithm relation, which is finally this C contact rate come up being the logarithm of the size of the urban center, okay, of the functional urban area. Again, coming back to the result for the US, again, are not linear population logarithm, data, and the fitting. This fitting now numerically I like in the second way, in which I put in evidence that it's 1 plus something. And this plus something, like, because it's the logarithm of n divided by some number, means that if n is this number, this will be 0 and R0 will be 1, and this is the threshold for the beginning. So a corollary, or I mean, a by-side product of this is that for sizes for urban centers which are smaller than this number on the denominator, we will not expect any propagation, any growing of the epidemic. Of course, this is not always the case, because we have a lot of dispersion of points here, okay? Now, some old results that we did before aggregating the data in the functional urban areas. Here we can see for United States, Brazil, Germany, and Portugal, results in terms of cities. So this is not functional areas. So for when we consider the sizes of the city, we can see that there is a large dispersion of points. Even there is a trend, there is a large dispersion of points. When we consider functional urban areas for the 6 countries that I'm showing here, Brazil, United States, Mexico, Czech Republic, Great Britain, and Netherlands, we can see nice plots, linear plots, and less dispersion here for Brazil than before. And the dot point here is the largest functional area. This is mainly the biggest city on the surroundings, okay? And we have a nice correlation coefficient, bigger than 0.7 for all the cases. Now, some explanation for this dispersion around the linear trend, the main trend. here we are representing the marginal deviation, how the points are dispersed above or below the fitting, and in terms of the residential percent change, which is measured by mobility. So when people stay at home, I mean, with the change in mobility is larger and larger, we can see that the points are below the curve, and we see the opposite when there is a negative residential percentage, which is more people moving than in these cases. So this is a nice crossing of these two things, the scaling and the mobility. So arriving at the end, we have this universal law, which is numerically in the case of the US in this form, a minimum size that comes after byproduct. And one message is that larger cities should prepare better. I mean, better means that more than proportionally. This is a specific valid for vaccination and any other measure that we take for controlling any epidemic. So final word, this is how this can be extended more than the or not. This is, I mean, how this expressed in other measures. For example, this is death per capita until July of the year. We can see that again there is a death per million here and population in log scale. This is not a clear log linear, linear relation here, but it's very. It tells us that again this is expressing somehow a result of what I showed you before. Okay, thank you very much.
Obrigada, Sebastián. There is a question in the chat. Can you see? Patriush Kumar asks, was the population density rho assumed to be the same in all regions?
No, it was not assumed. This is a good question because I didn't have time to open this part. But I mean, to say it the truth, when we perform this Midfield analysis, at the end we can take the two paths. We can go to the logarithm of n, or we can go to the logarithm of the density. The both are possible results of this simple network theory. Okay, so this is a flaw, you can say, of the theory. But when we check the data for almost every country, you can see that the scaling of in terms of the size is much better than in terms of the density. So the question is not, the density is not assumed the same, and there is a dependence with the density, and there is a dependence of size. In the case of United States, it's a strange case. I mean, somehow, because you can see almost the same good scaling with density and with size. It's like for United States, what is constant is the size of the city. So there is a typical size, and when you put more people, you are increasing density. It's like cities grow vertically. But this is almost only valid for United States. Okay. I don't know if
okay, thank you. Thank you very much, Sebastián, and all the speakers up to now today. We will restore the schedule and shorten a little bit the break now, so that we restart at 10:45 with Fabiana Lacuna's talk. Okay, so in this break, you can also make some pending questions.